A long, long time ago, back before fish, when almost all that existed was shellfish, a group of shellfish called bivalves today because their heart had two valves, had a problem. They fed through siphons, and despite the fact that the shellfish didn't move very much, they were subject to strong currents when storms raged above their beds and underwater currents literally picked them up and dropped them somewhere else. Because they couldn't choose where they fell or at what angle, they developed an evolutionary advantage to being able to turn themselves over so that their siphon wasn't fouled. Eventually, they developed an organ called the statocist that let them detect the angle of gravity. The statocist is a spherical organ that measures the angle of gravity. It consists of a spherical arrangement of hair-type nerve cells with the hairs to the inside, and a statolith, gypsum particle that acts to bend the hairs to measure gravity. My name is Graham Smith, and I'm an expert in artificial consciousness. If my theory is correct, we can blame consciousness on this first generation of bivalves that had statocists because it required a specific brain architecture to deal with the problem of righting the shell after a storm. As a result of the evolution of that brain architecture, later evolution resulted in consciousness. The seeds of consciousness have been with us for a very long period of time, and many other species have been born and died since, but relatively few have had the leverage of human consciousness to change their world. We are still confused as to what consciousness is, and why humans have more of it than any other animal. During this series of videos, I hope to familiarize you with the integrated model of consciousness and to introduce the idea that consciousness evolved over a long period of time, and it's not likely we will luck into a copy of it in computers in the short run, or that it's a field effect, as many would claim. During this series, I will introduce the idea that we can copy the biological systems of the brain with digital logic or with neural networks and begin to develop architectures that trend towards consciousness as we capture the essence of the brains of early animals to model the systems that will make consciousness as we know it possible in machines. The first project I'd like to introduce you to is the Toy Shellfish project. This project costs about $60 plus shipping. In this project, we'll be experimenting with the necessary programming to turn a machine over when it's turned on its side or upside down. This is a little like the plastic toy box novelty that was invented years ago, where you turned a box with this side up written on it on its side, and a foot came out of the box and turned it back right side up again. There's nothing more than startling novelty and a little engineering about the original plastic toy, but we were interested in the software needed to implement it in the computer. For this project, I've chosen 4 devices from Adafruit. A Feather 32U4 is the computer, an MMA 8451 accelerometer to implement the statocist organ, a fully assembled pen and tilt assembly, and a continuous micro servo. The ground pin goes into the 4th pin on the computer and the 1st pin on the accelerometer. The power pin goes into the 2nd pin on the computer and the 2nd pin on the accelerometer. The SDA pin goes into the last pin on the computer and the second last pin on the accelerometer. The system clock goes into the second last pin on the computer and third last pin on the accelerometer. Essentially, we hook up the accelerometer, load the software into our Arduino IDE, and it creates a library that we can use to read the accelerometer. We load the serial monitor and watch the outputs as it reads the accelerometer. The output we're interested in is the rectangular coordinates of the acceleration, which is expressed as 3 magnitudes in meters per second squared. This is a three-dimensional coordinate system. It's expressed in magnitudes in x, y, and z axis. To find the direction of gravity, we first wait for evidence that the accelerometer is settled. Essentially, this happens when the results stay steady over a short period of time. One of the problems with the MMA 8451 is that it's too sensitive and doesn't stay steady over a short period of time, even if the point of gravity doesn't change. In order to overcome this problem, I choose to average over a number of readings. As the number of readings in the average goes up, it stabilizes much better. Then we calculate the unit vector from the rectangular coordinates to get the direction of gravity. Finally, we convert to spherical coordinates to get the angles. It's useful to note that the staticist organ in these early mollusks is a sphere, so we get a point on a unit sphere as our result. The important angle for writing the toy is phi, which determines the angle from vertical. The other angle, theta, determines what angle the foot must push to economically write the toy. By calculating the spherical coordinates of the unit sphere, we have essentially done most of the work to make it possible for a robot to balance and therefore write itself. We must still throw away aberrant results, but the theory should work. If you've installed the MM8451 library properly, under the Files menu, when you start up the Arduino IDE, there's an example menu item. Hover over that and a submenu appears with the standard examples menu. At the bottom is a down caret which opens up the alternative examples menu, which includes the MM8451 examples menu item. Hover over this and the MM8451 demo menu item appears. Select this and you will get the MM8451 demo sketch on the screen. I had to track down the wiring library under hardware in the program directory to get my machine to compile, because it was complaining that there was 2 versions of wiring loaded. This is probably because I've loaded Arduino multiple times in different versions and they're not compatible with each other. Once you've compiled and verified the sketch, you can load it. I found that waiting until you've just repeated the compile step and then pushing the reset button on the Feather 32U4 restarts the bootloader program for you, and it will work with the Feather bootloader program. It's a little bit flaky, but I get semi-consistent results. Once you've successfully loaded the sketch, go to the Tools menu and click on the Serial Monitor menu item. This should start the serial monitor so you can read the serial bus. If you're getting a cluster of lines of data every few seconds, then it's working. What we want is the interpreted line of data, not the raw data or the words that tell you what position a phone would be in if it had the same clip in it. For your interest, I have edited the basic MMA 8451 demo file sketch to isolate the important parts and called it MMA 8451 demo-raw. This is available from my website http://theexperientialloop.ca. The link will be below in the descriptor. As you can see, most of the file is the same. but I've commented out the areas having to do with the raw data and the orientation. All that's left is the interpreted data. Now that we've isolated the important line of data, let us pre-program it to allow us to work with the results. The problem is that Adafruit has dumped the data directly into the serial bus without stopping for variables. So let us factor out a float value that has the basic information. Note, if you're interested in accuracy, you might want a double rather than a float, but I'm only interested in the angle of gravity, not the accuracy of the accelerometer. Spurious accuracy doesn't impress me. For your interest, I have edited the basic MMA 8451 demo and added the float variables to illustrate how to read the data. I call it MM8451 demo with floats. This is available from my website, http://theexperientialloop.ca. The link will be below in the descriptor. As you can see, there's really only one line difference between this and the previous file, other than the fact that I've gotten rid of the comments, where I commented out the uninteresting parts of the data. The next problem to deal with is the fact that the MM8451 is too sensitive. All it takes is to leave the breadboard relatively untouched for a short period of time, and we can see that the accelerometer doesn't settle, it keeps on changing its readings. No two readings in a row are similar, so we can't read a steady angle for gravity. To get around this, we need to do something I call undersampling, where we dull down the sensitivity of the chip by averaging the results over time. Worse, we get drop through, where the firmware reading the chip drops out and leaves the unmodified raw data on the serial bus. So we need a sentinel to throw away out of range data. We're using the chip in the 2G range, so our maximum value is 2Gs, or around 19.6 meters per second squared. For your interest, I've edited the basic MM8451 demo file sketch and added float array for averaging. Then I do some tests to act as sentinels for dropouts of the interpretive firmware. I call it MM8451 averaging demo. This is available from my website, http://theexperientialloop.ca. The link will be below in the descriptor. That's enough for a first video.